When you picture the absolute cutting edge of material science, I think your brain likely conjures up a very specific image, right? Like you're probably imagining this pristine multi-billion-dollar clean room in Silicon Valley or maybe.
Right, or like a classified military-industrial complex with people walking around in those heavy, positive pressure suits.
Exactly. Yeah, we have this ingrained, almost cultural assumption that the materials of our future must be completely synthetic, like entirely divorced from the messy reality of nature.
Yeah, we totally do. The prevailing mindset has, it's long been that innovation means bending atoms to our will through, brute force, astronomical budgets, and historically highly toxic refinement
Yeah,
processes.
right. Like we synthesize, we extract, we pollute to create our advanced tech. But today's deep dive, it subverts that assumption entirely.
It really does. It completely flips it.
Yeah. So we are looking at this remarkable doctoral dissertation from the year 2026, and it's accompanied by a set of incredibly detailed lab notes from a guy named Martin Gutierrez Guerrero.
Yeah, he's a Costa Rican researcher and the CEO of an applied engineering company called Nova Amazonia.
Right. And the mission for our exploration today, what we're really digging into, is unpacking how they are taking literal agricultural waste.
Which is just wild.
It is. Specifically, the dead, pruned branches of coffee bushes gathered from Costa Rican mountainsides and transforming them into a supermaterial. We're talking about a biofabric that conducts electricity, has tensile strength surpassing Kevlar, and, honestly holds the very real potential to restructure the entire global supply chain.
It's incredible. And the overarching framework we see in these sources is a concept known as deep biomimicry.
Right, deep biomimicry, which is different from just regular biomimicry, right?
Exactly. This is far beyond, say, copying the aerodynamic shape of a bird's wing to build a better jet. This involves recognizing how natural ecosystems have already solved incredibly complex nanoscale architectural problems over, well, millions of years of evolution.
Right, because nature's been running the ultimate R&D lab forever.
Exactly. And by identifying and leveraging those ancient biological solutions, this research demonstrates a pathway to bypass all that destructive rare earth mining and silicon processing that currently bottlenecks modern tech.
Okay, so before we step into the nanotech laboratories, we really have to establish the biological foundation here. Because out of the estimated hundreds of thousands of plant species on Earth, the sources focus intensely on commercial varieties of Arabica and Robusta coffee, grown specifically in Costa Rica's Central Valley.
Yeah, which immediately begs the question, why there? Why does that specific geographic location act as the catalyst?
Right. It comes down to the fact that geography fundamentally dictates biology.
It does. From an evolutionary perspective, the Central Valley of Costa Rica operates as this intense laboratory of environmental stress. These coffee plants cultivate at altitudes ranging between 800 and 1,600 meters above sea level, positioned right along an equatorial latitude.
So that altitude and latitude combination, it means they're just blasted with intense UV radiation throughout the day.
Yeah.
But the specific stressor driving this entire adaptation, the really important one, is the thermal oscillation.
The temperature shifts are brutal. We're looking at environments where the temperature can plummet 15 degrees Celsius in a window of just 6 to 8 hours as the sun goes down over the mountains.
Which is a massive swing.
It's huge. And that kind of rapid thermal drop presents a major mechanical crisis for a plant. To understand the severity, you really have to look at the physics of plant hydration.
Right, how the plant drinks.
Exactly. A vascular system in a tree or a bush, it operates on negative tension and cohesion. So as water evaporates from the microscopic pores in the leaves, it creates this powerful suction.
It's basically drinking from a giant straw.
Yes, that suction pulls continuous microscopic columns of water up from the soil through the roots and into the branches.
So it's an internal system operating under extreme tension. But when those temperatures drop 15 degrees in an afternoon, or say during periods of severe high-altitude drought, the tension acting on those microscopic water columns spikes to just an unbearable level.
Right.
And for those listening, you have to understand, this goes far beyond a biological inconvenience for the shrub. Like, it's a lethal mechanical physics problem.
It's a life or death situation for the plant. The tension crosses a critical physical threshold where the water column actually snaps.
Yeah.
The cohesive force holding the water molecules together it fails under the strain.
Yeah, and the lab notes refer to this Mechanical failure as cavitation.
Cavitation,
The
exactly.
water column breaks,
Huh.
and that immediately creates a microscopic air bubble within the vascular tissue.
Hmm.
And once that void forms, it operates as a permanent roadblock.
Yeah, the water can no longer flow past the bubble, and that entire section of the branch inevitably dies.
It just cuts off the supply.
Yeah.
So over centuries of enduring these specific mountain microclimates, the coffee bush had to engineer a defense mechanism against that constant threat of cavitation.
It had to adapt or die out.
Right. And it adapted by altering its internal microscopic architecture. It developed cellular walls that organize into a nearly perfect hexagonal network,
It basically builds a microscopic honeycomb.
which makes sense because the hexagonal shape is an incredibly efficient distribution mechanism.
It really is. It allows the plant to pack the absolute maximum number of vascular conduits into the smallest possible cross-section of the branch. That geometry distributes the massive negative pressure evenly across the cellular structure.
Right, so it's preventing the water columns from collapsing under the thermal stress.
Exactly. It's the exact same architectural efficiency we see in a beehive, but, applied to the fluid micromechanics of a mountain shrub.
Which is amazing. And that evolutionary adaptation brings us to the master concept underpinning the entire Novi Amazonia dissertation. The researchers call it geometric isomorphism.
Geometric isomorphism. This is where the story gets really wild.
Seriously. So when the researchers placed this hexagonal coffeewood structure under an electron microscope, they discovered it was a perfect topological match for graphene.
And just to pause there, graphene is essentially the holy grail of 21st century materials engineering.
Right.
It is a single layer of carbon atoms, precisely one atom thick, naturally organizing itself into a two-dimensional hexagonal lattice.
And the mathematical proportions of the plant cells mirror the atomic structure of that graphene. Like the angles of connection, the 60 and 120-degree intersections of the structure, they're perfectly analogous.
Right. And when we look at the scale, the implication of that match is just enormous. Because the carbon atoms in graphene are measured in angstroms, which is an incomprehensibly tiny metric.
Super tiny. But the hexagonal cells in the coffee wood, those are measured in micrometers. They are massively larger.
Yeah, it's a completely different scale.
Let me use an analogy here for you listening to really visualize this scale difference.
Yeah.
Imagine a team of structural engineers analyzing the rustic wooden scaffolding used to construct a massive barn like a century ago. And suddenly they calculate that the angle, the geometry, and the ratio of every single wooden beam in that barn mathematically matches the precise internal molecular lattice of a diamond.
That's a perfect way to describe it. The geometric template is identical. It's simply expressed at vastly different magnitudes.
Right.
And the industrial implications of this isomorphism are profound. Because in traditional semiconductor and advanced materials manufacturing, growing 3D graphene and maintaining its structural integrity requires an underlying template. Industry relies on ultra-pure silicon substrates or exceptionally expensive rare earth metals to provide that scaffold.
Which, that requires aggressive mining operations, massive financial capital, and extensive toxic chemical refinement just to prepare the substrate.
Exactly. But here, biological evolution has provided a perfectly pre-designed geometric template in the form of discarded agricultural biomass. The coffee wood naturally serves as the scaffold.
Which sounds flawless in theory, right?
Yeah.
But applying it seems incredibly volatile, because a living branch is packed with sap, biological resins, moisture.
Right, it's wet.
Yeah, it's full of water. So if you subject that raw biomass to high heat to dry it out, you're going to create a massive pressure differential. The water trapped inside those microscopic honeycombs would boil, expand into steam, and instantly shatter the fragile cellular walls from the inside out.
It would just destroy the structure. Traditional thermal drying causes exactly that. The lab notes actually define it as hydraulic detachment.
Hydraulic detachment. Okay, so how do they bypass that?
Well, the researchers employ highly precise stepped microwaves. Instead of applying external heat that slowly penetrates the wood, the microwaves target and excite the water molecules directly and uniformly throughout the entire cross-section.
Oh, wow. So the moisture evaporates molecule by molecule in controlled stages.
Exactly. It entirely avoids the violent internal pressure differentials, so the hexagonal scaffold survives completely intact.
Okay, so you've removed the water without destroying the architecture.
Yeah.
But you still have a branch full of volatile biological compounds that will definitely interfere with graphene synthesis. You need a pure carbon skeleton.
Right, you need to strip away everything else, and they achieve this through selective pyrolysis inside a completely inert atmosphere.
Pyrolysis. So they put the dry biomass into a thermal reactor at 800 degrees Celsius. But my question when I read this was, why doesn't it just burn to ash?
Because the reactor is flooded with pure nitrogen gas, which eliminates combustion entirely. No oxygen means no fire.
Ah, right.
So instead of burning, it undergoes thermal degradation. The natural resins and hemicelluloses volatilize and evaporate, leaving behind a perfectly preserved biocarbon skeleton.
And the physical properties of that resulting skeleton completely redefine surface area. This part blew my mind. Because of the dense, porous hexagonal geometry of the original plant, just 1 single gram of this purified biocarbon.
Which is roughly the volume of a standard sugar cube.
Yeah, a sugar cube. That tiny piece contains an internal surface area of 420 square liters. You're looking at the footprint of a professional basketball court packed into a sugar cube.
It's hard to even wrap your head around, but that massive internal surface area becomes the reaction chamber for chemical vapor deposition, or CVD.
Right, the CVD stage.
Yeah. They inject hydrocarbon gases, specifically methane or hydrogen, into the reactor and elevate the temperature beyond 1,000 degrees Celsius. The intense thermal energy literally fractures the methane molecules, stripping the hydrogen away and leaving highly energetic carbon atoms floating freely.
And those carbon atoms are highly unstable in that state, right? Like they are desperately seeking a structure to bond with to stabilize.
Exactly. And the geometry forces their hand. Because of the geometric isomorphism we established earlier, when those free-floating carbon atoms drift into the biocarbon skeleton, they encounter a hexagonal template perfectly aligned with their own topological preference.
So they naturally auto-assemble.
Exactly. The atoms deposit themselves in perfect order across all 420 square meters of that internal surface area, growing seamless 3D graphene directly onto the coffee mold.
It's auto-assembly on a massive industrial scale. You aren't forcing the atoms. You're providing the blueprint they naturally want to follow.
Right.
But the dissertation highlights another crucial engineering hurdle. Pure graphene possesses a Young's modulus of 1 terapascal, which means you could balance the entire weight of an adult elephant on the tip of a pencil, and the single layer of graphene underneath would not yield a fraction of a millimeter.
Which is incredible strength, but maximum rigidity is actually an inherent mechanical vulnerability.
Right, because a material with absolutely zero flexibility is functionally useless for dynamic applications.
Exactly. Pure graphene is incredibly brittle. If you take that perfect lattice and bend it by even 0.5%, the mechanical tension shatters its covalent bonds. The material cracks, and the electrical conductivity is instantly severed.
Yeah, you can't build clothing or aerospace suits out of something that shatters when the wearer bends an elbow.
No, you can't. So to solve this, Nova Amazonia introduces a hybridization phase using multi-walled carbon nanotubes. They weave these microscopic nanotubes throughout the graphene matrix to serve as transverse anchors.
So they operate like microscopic elastic suspension bridges spanning the gaps across the graphene lattice. If the material undergoes physical stress and a microfissure occurs in the graphene, the nanotube anchors maintain the structural connection.
Right. They absorb the tension and ensure the electrical current continues flowing without interruption across the microscopic gap.
That is brilliant. And this integrated material is what they designated biotella de café, coffee biofabric.
Yeah. And by incorporating these nanotube bridges, the fabric can stretch up to 30% of its original dimensions while fully retaining both its structural integrity and its conductivity.
30%, that's huge.
It is. And the researchers then integrate this dynamic matrix with their proprietary AI ecosystem, PRONLNK369AI, which they refer to as Galatea.
Okay, so let's talk about what they're actually going to do with this stuff. Because when you analyze the sheer scale of the aerospace projections in the dissertation, the implications are just staggering.
Oh, absolutely.
The structural math demonstrates that a single thread of this coffee biofabric, measuring just 10 micrometers thick,
Which is thinner than a human hair and barely visible to the naked eye.
right, that single thread can sustain a tension load of 2,000 kilograms. You could suspend a large commercial vehicle from a single microscopic thread.
It's mind-boggling. And the extravehicular activity suits, or spacesuits, are a perfect application of this paradigm shift because current orbital infrastructure relies on essentially archaic, rigid spaceships tailored to human shapes.
Yeah, they're super bulky.
They are 180-kilogram pressurized frames, and a significant portion of that mass is simply internal fluid dynamics, miles of tubing pumping water continuously to regulate temperature, preventing the astronaut from freezing in the orbital shadow or boiling in direct solar radiation.
Right, it's like wearing a heavy plumbing system. But the biofabric renders those heavy water cooling systems obsolete through a thermodynamic property called thermal anisotropy.
Exactly.
Because of how the carbon atoms are structured within the hybridized matrix, the fabric conducts kinetic energy heat rapidly across its horizontal surface. However, vertically, passing through the internal layers toward the wearer, it acts as an absolute thermal insulator.
Right. So when unfiltered solar radiation bombards the exterior of the suit, the layered graphene structure completely rejects the thermal transfer inward toward the astronaut's skin.
It captures that intense thermal energy and channels it horizontally along the exterior surface of the fabric, migrating the heat entirely to the dark side of the suit, the side facing the dead freeze of space.
So the suit basically operates as a passive solid-state radiator.
Yeah, there are no moving parts, no heavy water pumps, and no mechanical failure points.
And it gets even better. Because the carbon nanotubes alter their electrical resistance as they stretch, the physical expansion of the astronaut's chest during breathing alters the conductivity of the suit itself.
Oh, wow.
Yeah, the Galatea AI system uses the entire surface area of the fabric to monitor respiration and heart rate. The suit basically functions as an integrated, non-invasive sensory nervous system.
That is insane, and that exact same structural matrix translates directly to unprecedented terrestrial biosecurity, too. The sources detail extensive applications for Level 3 and Level 4 biolabs, where researchers interact with highly lethal pathogens like Ebola or Marburg virus.
Right. Under current safety protocols, scientists rely on thick, positive pressure polymer suits. And a fatal breach usually isn't a massive tear. It's an accidental brush against a contaminated hypodermic needle.
Yeah, just one microscopic puncture through the plastic is catastrophic. But the density of the hybridized biocarbon matrix is completely impenetrable to the kinetic force of a needle. It acts as an incredibly lightweight, flexible kinetic armor.
It does, and it also maintains chemical inertness, meaning it is entirely unaffected by the harsh liquid decontaminants heavily utilized in those environments, like concentrated hydrogen peroxide, which normally degrades traditional synthetic polymers over time.
Now, when reading the source material, I immediately looked for the catch regarding breathability. Because a material dense enough to stop a needle and chemically block liquid decontaminants should theoretically suffocate the person wearing it. It sounds like magic. Yet, the text asserts it is highly breathable for extended shifts.
Yeah, the breathability circles back to the original architecture of the coffee bush thriving on the Costa Rican mountain. The original hexagonal pores of the plant establish the baseline gap sizes within the final nanotech matrix.
Right, the honeycomb.
Exactly. Those gaps operate on a sub-nanometric scale. They are geometrically sized to permit tiny water vapor molecules, so the astronaut or scientist sweat to pass cleanly through the structure. However, a virus operates on a completely different biological scale. A virus is a massive lipid-encapsulated entity. It is geometrically too large to physically fit through the hexagonal barrier.
So it's selective filtration.
Yes. Pure mechanical size exclusion filtration without sacrificing permeability for vapor.
That's amazing. I mean, you could manufacture kinetic and biological armor as light and pliable as a standard windbreaker jacket.
Exactly. And beyond defense and aerospace, the expert notes delve deep into large-scale energy harvesting, specifically detailing the piezoelectric effect.
Right.
You could wrap the massive composite blades of commercial wind turbines in this biofabric. As the massive blade flexes and deforms under the stress of the wind, that physical manipulation warps the crystal lattice of the embedded carbon nanotubes.
And that deformation creates a dipole moment, right? It forcibly displaces electrons and turns ambient mechanical stress directly into a massive secondary electrical current.
It does. And the thermodynamics scale even further when applying the Seebeck effect to industrial infrastructure. Like, imagine wrapping a heavy factory pipeline carrying superheated industrial fluids in this material. You have an extreme temperature gradient. The boiling heat of the pipe on the inside and the cold ambient air on the outside.
Right, so that thermal contrast essentially agitates the electrons on the hot side of the lattice, increasing their kinetic energy and forcing them to diffuse rapidly toward the colder, less energetic side.
Exactly. And because the coffee biocarbon provides that staggering 420 square meters of internal surface area per gram, the efficiency of this electron migration is exponentially amplified. It generates a constant heavy flow of static electricity simply by existing in a state of continuous thermal contrast.
The factory pipeline generates power just by remaining hot. That's incredible. And the maritime applications follow a similar logic of leveraging the surface physics, right?
Yeah, the graphene network is so molecularly smooth that it lacks the necessary microscopic friction points for biological adhesion.
Right, so if you apply this material to the hull of a massive cargo ship, sea barnacles, algae, and microorganisms physically cannot find a texture to latch onto.
Exactly. It solves a massive logistical issue of biofouling. This simple structural smoothness could eliminate the global maritime industry's reliance on the millions of liters of highly toxic, heavy metal anti-fouling paints that continuously leach into and devastate marine
Now,
ecosystems.
that'd be revolutionary. Now, when you aggregate all these applications, you inevitably hit the geopolitical core of the dissertation, right? The geoeconomic reality.
Yeah, this is the really powerful part. All of these advanced capabilities are inextricably rooted in the harsh agricultural economics of the global south. Look at the operational realities of the current commercial coffee market. The farmers' entire generations of communities across Costa Rica, Colombia, and sub-Saharan Africa absorb 100% of the operational risk.
Yeah, they shoulder the devastation of agricultural plagues, the increasing severity of droughts driven by climate change, and the brutal, unpredictable volatility of global stock market pricing.
And in exchange for absorbing that totality of risk, the financial value that returns to the origin point is staggeringly low, typically less than 7% of the final price the consumer pays in a cafe.
Wow, less than 7%.
Yeah. Traditional agricultural economics dictate that a highly optimized, well-managed hectare of coffee might yield an annual return of roughly $5,000 from the sale of roasted beans.
Right. And to maintain the health of the bushes and ensure bean production, farmers have to aggressively prune the plants every cycle. Historically, the tons of dead branches generated by pruning represent a massive logistical burden.
It's agricultural waste.
Exactly. Farmers expend capital and labor to gather it, usually burning it in open-air pits, which releases heavy carbon emissions, or they just leave it to rot. It literally carries a negative financial value.
But Nova Amazonia's methodology completely inverts that economic equation. By recognizing the inherent structural value of the wood's geometry as a high-tech manufacturing template, the perceived waste instantly becomes infinitely more valuable than the primary crop.
Because the economic projections detailed in the report, they represent a total paradigm shift. When processed through these precise stages into the functional biofabric, the pruned branches extracted from a single hectare of coffee possess an estimated potential market value of $2.5 million per harvest cycle.
It's an unbelievable jump. The revenue stream goes from $5,000 for the consumable beans to $2.5 million for the discarded wood.
And this dictates a tectonic shift in the geopolitical flow of technology.
Yeah.
Because historically, the pipeline of innovation is strictly unidirectional, right?
Exactly. It's funded, conceptualized, and synthesized in the global north, in the technological hubs of Silicon Valley, Shenzhen, or Taiwan, and subsequently exported outward.
Right.
In this scenario, the intellectual capital of Martin Gutierrez Guerrero and his engineering team synchronizes with the endemic natural capital of Costa Rica. They are establishing the framework to export the absolute frontier of aerospace, defense, and clean energy materials directly from the global south.
And they are actively resisting the urge to hoard the technology behind proprietary walls, which is super refreshing. The documents outline the launch of a Centro de Especialización del Café, a dedicated training center designed specifically for local farmers and the next generation of their communities.
Yeah, the curriculum focuses on advanced biomass utilization, agricultural nanotechnology, and the management of a carbon-neutral bioeconomy.
So they're providing the infrastructure to transition communities historically confined to vulnerable subsistence farming into the strategic materials engineers overseeing 21st century infrastructure.
It represents the ultimate realization of a closed-loop bioeconomy. The manufacturing relies on processes devoid of combustion. The raw material actively absorbs atmospheric carbon dioxide during its growth phase on the mountain, and the entire supply chain circumvents the devastating ecological impacts intrinsically tied to traditional rare earth metal extraction.
It's amazing. We began this exploration looking at a seemingly ordinary coffee shrub clinging to the side of a Costa Rican mountain, desperately evolving microscopic honeycombs in its branches, purely to survive the brutal mechanical stress of freezing nights.
Right.
And buried within that desperate biological adaptation was the precise architectural blueprint required for space-age tension cables, impenetrable biological armor, and the potential restructuring of global economic wealth.
It serves as a stark reminder that the most advanced technology on the planet might just be the natural world we've been burning as trash.
Exactly. It clearly reinforces the idea that true innovation isn't solely about synthesizing something entirely novel in a vacuum.
Yeah.
It is often about cultivating the perspective to realize that a complex problem was already elegantly solved millions of years ago.
Absolutely. Nature already did the hard work.
Yeah. So I want to leave you with one final, slightly provocative thought, directly inspired by the staggering economic projections laid out in the dissertation. If the previously worthless, pruned dead wood of the coffee bush is fundamentally destined to become the multi-million-dollar backbone of global aerospace and energy infrastructure, wait, what ultimately happens to your morning cup of coffee?
Oh, wow. That's a fascinating point.
Right? If the true geopolitical power and immense economic wealth of the plant lies entirely in its wooden geometry, is it possible that the famous dark drink that has fueled global human productivity for centuries will soon be reduced to nothing more than a cheap residual byproduct of a massive agricultural technology empire? Something to chew on the next time you step over a fallen branch. Thank you for joining us on this deep dive, and keep questioning the world around you until our next exploration.